This Transactions on Robotics paper describes the modeling, analysis, and actuation-based force sensing for parallel continuum robots. The work was supported by the National Science Foundation through the National Robotics Initiative. Parallel continuum robots combine the compactness, simplicity, and compliance of continuum robots with the precision and strength of rigid-link parallel robots. The parallel continuum robot shown in this video is a Continuum Stewart Go platform which uses 6 flexible rods attached to independent linear actuators to achieve 6-stop control of the end effector. In this paper, we provide a generalized Coursera rod-based kinetostatic model framework that accommodates various joint types and problem formulations used for simulation and control. The Coursera rod static equilibrium equations describe the overall shape and internal forces of each flexible link. These individual link models are coupled through distal and proximal boundary conditions, which depend on the joint types used at the proximal and distal ends. The resulting system of link models must be solved simultaneously to obtain the static equilibrium shape of the entire robot. We use an efficient shooting method to solve for all the model outputs and unknown proximal boundary conditions. By simply changing which set of variables are specified and which sets are unknown, this framework can seamlessly solve various useful problems such as the forward kinematics under known loads, inverse kinematics under known loads, deflection-based force sensing, and actuation-based force sensing. Linearization of this general model provides the manipulator Jacobian, end effector compliance, input stiffness, and wrench reflectivity matrices, which allow us to examine the effect of design parameters on dexterity, force application, and force sensing ability. Using ellipsoids based on the matrices, we provide a set of design simulations and graphically depict the dexterity, compliance, and force sensing ability of a typical design. Based on model simulations, we also provide a non-dimensional analysis of the compliance of parallel continuum robots with respect to changes in robot radius, length of the flexible links, and angular separation of the links. Finally, we experimentally demonstrate and validate the actuation-based force sensing model on a prototype 6 degree of freedom parallel continuum robot with actuator-mounted force sensors. This model takes in measured actuator forces and actuator displacement and predicts the end effector pose, deformed shape of the compliant legs, and the end effector wrench. The experimental 3D force sensing results show median magnitude and directional errors of 8% and 12 degrees respectively.